Now we're going to the next talk, which is from Iman Marvian. And so, yeah, we're going to speak of symmetry and locality in quantum thermodynamics. Okay, so Iman, please, if you are ready, you can start sharing your screen.
Sure. Okay. Okay, can you see my presentation?
Yes.
Perfect. Yeah, thanks a lot, Ilya, for the introduction, and thank you to Camille, Ilya, and Francesco, the organizers, for organizing this nice workshop, and also for inviting me and giving me the opportunity to present my work. So my name is Iman Marvian. I'm an assistant professor at Duke University. I work on different aspects of quantum information theory and its application in quantum thermodynamics. It's certainly one of my main research interests. In this work, I'm presenting a series of related ideas and results on different aspects of symmetry and locality in the context of quantum thermodynamics. So the talk has two main parts. So in part one, I focus on time translation symmetry and basically study or describe the consequences of time translation symmetry in the context of quantum thermodynamics. For example, I will talk about how we can quantify coherence. I will talk about the framework for quantifying coherence. And I also talk about coherence distillation in the context of quantum thermodynamics. And in the second part, I will talk about locality. And in particular, I asked the question, how we can implement a general energy conserving unitary using local interactions that also respect the symmetry, or in other words, they conserve energy. So I prove a no-go theorem, and then I show how we can circumvent this no-go theorem. Okay, so let me start. Part one is about time translation symmetry in quantum thermodynamics, and let me start by reviewing, the well-known connection between symmetry and conservation laws, which is a very powerful tool in physics in general, and also in quantum thermodynamics. And so the idea is usually, basically the most general version of the idea maybe is described by Noether's theorem, that says, roughly speaking, there is a connection between continuous symmetries of a system and conserved quantities. In particular, for any continuous symmetry, there is a conserved quantity. Now, in the context of quantum thermodynamics, which is the focus of this talk, this, for example, implies that if you implement a unitary transformation that commutes with the time translation symmetry, then you should expect a conservation of energy. So to be more precise, let's consider a closed system with an intrinsic or free Hamiltonian H and a unitary transformation U. Then if this unitary U commutes with this unitary e to the minus IHT that generates time translation, then we know that U leaves Hamiltonian, this free Hamiltonian invariant. U, H, U dagger will be equal to H, which is basically the statement of conservation of energy. By the way, this family of Hamiltonians that leave the free Hamiltonian of the system invariant, family of unitaries that leave the intrinsic Hamiltonian of the system invariant, I will call them energy conserving unitaries, and this will be a related topic also in the second part of the talk. So energy conserving unitaries are those that leave the intrinsic Hamiltonian of the system invariant. Now you can see that if you have this kind of symmetry, and if you have this kind of conservation laws, then you can put a lot of constraints on the possible transitions that can be realized by this kind of energy conserving unitaries. For example, if there exists an energy conserving unitary that transforms states rho to sigma, then we know that energy is conserved, which means that the expectation value of energy is conserved, but also all moments of the this free Hamiltonian H are also conserved. So for any integer n, trace of H and rho is equal to trace of H and sigma. All moments of energy are conserved. Okay, so this is nice. It's a very powerful tool in to study closed system dynamics. But the notion of time translation symmetry can also be generalized to the more general case of open system dynamics. So in general, consider a general open system time evolution under which initial density operator rho evolves to E rho. So this is a linear map, and it's we know there's completely positive trace preserving, but for the purpose of this slide, it doesn't matter. There's completely positive trace preserving. And now if I assume that this system also has an intrinsic or free Hamiltonian edge, then I can also think about time translation on this system generated by the intrinsic Hamiltonian edge. So let's say if under this time translation, rho evolves to e to the minus IHT, rho e to the IHT. This is free evolution of the system. And then you say that this map E is translationally invariant, or TI. It respects the time translation symmetry if basically this diagram commutes. If you first apply the map E and then evolve it under its free Hamiltonian, the final result should be exactly equal to if you go the other way around. You first let the system evolve under Hamiltonian, free Hamiltonian, and then apply the map E. In other words, this equality should hold for all time t, and of course for all initial state rho. If a time evolution E satisfy this symmetry, I would say it's the TI operation. It respects the time translation symmetry. By the way, feel free to interrupt me if there are any questions. Okay. So an example of this TI operations is a family of operations that are called Telmar operations. This is a fundamental concept, especially in the context of resource theory of thermodynamics. So these are operations that you can implement on your system by coupling it to a thermal bath, which is, let's say, initially in a Gibbs state, by an energy conserving unitary. So I'm assuming that the total Hamiltonian of the system and thermal bath is just the sum, so they are not interacting with each other. The free Hamiltonians are not interacting with each other. And then a unitary U is energy conserving. It's commutes with this total Hamiltonian. And a general thermal operation is an operation that can be implemented in this way on the system. So you couple them by this energy conserving U and then discard the thermal bath. It's easy to see that this family of maps basically respect time translation symmetry. They are TI operations. And basically the intuition is, if you think about the steps here, you're coupling by this energy conserving unitary and discarding the thermal bath. These are all basically invariant under time translation. So it shouldn't matter that exactly when you do this coupling. And the state of thermal bath is also, I'm assuming that it's a stationary state, so it's not time dependent. And now the point is, so this family of maps have this, time translation symmetry, and we saw that time translation symmetry has a lot of consequences in the case of closed system. But the question is, what about the open system? So here, the connection between conservation laws and time translation symmetry is lost. You may have, in general, you may have, time translation symmetry without conservation, meaning that the energy of system is not in general conserved. Okay? So how we can find this consequences of symmetry in this case, basically? Or are there any non-trivial consequences or not? Okay. So a nice, application of the study of time translation symmetry is that it gives us a good framework for understanding and quantifying coherence. So here, when I talk about coherence, I mean coherence between different energy eigenstates and with different energies, basically. So in particular, I say a state is incoherent if it commutes with the intrinsic Hamiltonian of the system. And now you can easily see that this condition is equivalent to this condition in the right, that state is stationary under time translation. If e to the minus IHT rho e to the IHT is equal to rho for all time t. It's invariant under time translation. So these two conditions are equivalent. But this means that, to understand coherence, one way to think about coherence is to think of it as a breaking of time translation symmetry. And then you can ask how much, for example, this time translation symmetry is broken by a state. And that way you can quantify the amount of coherence in the state. Okay, so here are some examples. So if E0 and E1 are energy eigenstates with energy E0 and energy E1, distinct energy E0 and E1. So these are examples of incoherent states, and this is an example of coherent states, coherent state. And we want to somehow quantify the amount of this coherence. We want to have a framework for quantifying this. Okay. And a simple observation is that under TI operations, you cannot generate coherence. If your initial state is incoherent, commutes with the Hamiltonian, your final state should also be commute with the Hamiltonian. And this, again, can be easily understood based on this intuition that, TI operations or time translation invariant operations are operations that do not generate asymmetry with respect to time translations. And if your initial state doesn't have the time, any asymmetry with respect to time translations, and your time evolution, E, doesn't have that, then your final state should also doesn't have any asymmetry with respect to time translations. And basically, it follows that coherence, you can think of it as an independent resource from work. It's not, if you start with an energy eigenstate, for example, you can never generate a coherent state. And this has been, implications of this idea and generalization of this idea has been extensively studied in the resource theory of quantum thermodynamics, for example, in these papers. Okay, now I mentioned that TI operations do not generate coherence, but there are also non-TI processes that do not generate coherence. And here is an example. So suppose my Hamiltonian, the system is just a qubit and the Hamiltonian is just this. It's basically Pauli Z, Z is Pauli Z. So there's an energy difference delta E between these two eigenstates. And in this case, all incoherent states are states that are diagonal in 0-1 basis. And now if you think about the unitary Pauli X, it obviously leaves state invariant. Sorry, it obviously maps a diagonal state to a diagonal state. It doesn't leave state invariant in general, but it maps an incoherent state to incoherent state. And so it doesn't generate coherence. In other words, there are also non-TI operations that do not generate coherence. But interestingly, it turns out that if you think about a reference system and assume that the system, my system S here, for example, in this qubit is this, in this example is this qubit, can be entangled with the reference system A. And then you ask that, when you apply this operation and apply identity on your reference system, the entire, it should map this entire process, E tensor identity basically, should map an incoherent state to incoherent state. If you require this, then it turns out that the only maps that satisfy this property are TI operations, basically. So in other words, we can prove that an operation is TI, time translation invariant, if and only if it maps incoherent state to incoherent states, even if the system is entangled with the reference system. Okay. So here I'm assuming that the total Hamiltonian of the system and this reference system they are non-interacting, and they are initially in an incoherent state. I require that finally at the end of the process, they should still be in an incoherent state. So if you go back to this example, suppose I have another qubit with the same Hamiltonian, and this will be the total Hamiltonian, then this state 0 plus 1, 0, 1 plus 1, 0 is incoherent because it's an eigenstate of this. But if you apply Pauli X, the same map here, tensor identity, it maps an incoherent state to a coherent state. So, so this means that basically, in a way, TI operation is the most general processes that do not generate coherence if you consider this a reference system. And so I propose this name of completely incoherence preserving operations. And the word completely here should remind you how the notion of complete, how complete positive operations are distinguished from positive operations. So, sorry, I didn't realize that. Okay. So it turns out that, I talked about time translation symmetry, TI operations satisfy time translation symmetry. I talked about completely incoherence preserving operation. It turns out that there is another way to characterize TI operations. A TI operation in general is an operation that can be implemented on the system by coupling it to another system or battery that is initially in an energy eigenstate. And this coupling should be by an energy conserving unitary. I had a slide, and sorry, I had a slide on this, but I somehow looks like I moved it somewhere else. Sorry about that. Anyway, yeah. Okay, I jumped from this. So a general TI operation is not a thermal operation, but you can always implement a TI operation by coupling your system to an energy eigenstate by an energy conserving unitary. So here I mean that if you're given a general TI operation, you can always find an auxiliary system or a battery that is initially in its energy eigenstate and couple it to your system by an energy conserving unitary. So you should commute with the total Hamiltonian of the system and auxiliary, total Hamiltonian of the system and the auxiliary system. And the auxiliary system should be initially in the energy eigenstate. Okay. You can always realize an energy, a TI operation in this way. Okay. So intuitively, this means that if you are allowed to consume work, then you can implement any TI operation. But if you don't have this extra resource of a work reservoir battery, you cannot generate a TI operation just by thermal operations. Okay. And so anyway, so the point is that there's three different ways of thinking about the same set of operations. The set of TI operations, we can characterize them in terms of this kind of time translation symmetry. We can define them in terms of the set of operations that you can implement on your system by coupling it to a system in an energy eigenstate or battery by an energy conserving unitary. And you can also define it in terms of this notion of completely incoherence preserving operations, operations that do not generate coherence, even if my system is entangled with another reference system. These three definitions turn out to be equal. And basically, this explains why this set of TI operations are relevant, and they appear in many different contexts. There are different points of view to define exactly the same set of operations. Okay, so one application of this TI operations is basically to, as I mentioned before, to focus on the notion of coherence in quantum thermodynamics. So if we just want to focus on coherence and understand coherence, and we are not worried about work as a resource, then we can just focus on TI operations. And in this way, basically, we find a simpler picture about the notion of coherence in quantum thermodynamics. So this can be contrasted or compared with another point of view where you just say, I want to focus on, I want to ignore coherence and just focus on work. And then I just study classical states or states which are diagonal in the energy eigenbasis. So incidentally, this understanding, this family of TI operations and their more generally operations that respect the symmetry and the type of transitions that can be implemented by these operations is basically studying the resource theory of asymmetry. So resource theory of asymmetry is the study of this kind of transitions and the constraints that are imposed by the presence of symmetry. Okay. Please feel free to stop me if there are any questions as I go through the next part. Now, let's talk about a couple of examples of these constraints that I mentioned here. So the first type of constraints that you can characterize is based on the idea of measures of asymmetry. And in particular, here I focus on time translation asymmetry. So it's a particular, I'm focusing on a particular symmetry, the symmetry generated by the free Hamiltonian of the system. And in this sense, a measure of asymmetry is, you can also interpret it as a measure of coherence, because as I mentioned before, asymmetry with respect to time translation is equivalent to coherence. And now again, the intuition is time translation asymmetry or coherence is a property that cannot be generated by TI operations. So a measure of time translation asymmetry or coherence should be non-increasing under this type of operation. So that's the idea. And that's how we define it. So a measure of time translation asymmetry should satisfy this monotonicity. If rho can be transformed to sigma by a TI operation, then f of h, this is the monotone basically, this measure of asymmetry should be, for rho, it should be larger than or equal to f of h of sigma. So it should be non-increasing. And also you are required that this quantity should be 0 for incoherent states. So this is a property that the second property is not really essential, because from the first property you can show that any measure of any function that satisfies this property should take exactly the same value on all incoherent states, because basically from any incoherent state you can go to another incoherent state using a TI operation. So this just basically sets the minimum value of the a measure of asymmetry. So the main property is this monotonicity under TI operations, basically. Okay, so let me show you an example of these measures of asymmetry. Here is a famous function called Wigner-Janz Dyson skew information. So f of h of rho is given as -1/2 trace of square root of rho h squared. So note that to define a measure of asymmetry, you need to specify also the Hamiltonian of the system, because this is basically, H is the operator that defines the notion of symmetry. And so here we are quantifying symmetry breaking with respect to the time translation generated by this Hamiltonian. And note that if my state rho is incoherent, then this commutator is 0, and so this function vanishes. And in general, we can show that if rho is not incoherent, if it breaks time translation symmetry, then this function is strictly larger than 0. Now, this function has a very interesting story. As I said, it's introduced originally by Wigner and Janz in this paper from '63, and then later was generalized by Dyson. And it looks, if you look at the paper, it looks that they have some intuition. So they study basically what are the so the question that they want to understand is how the presence of symmetry restricts the type of information that you can obtain from a system. And they argue that somehow, von Neumann entropy or Shannon entropy will not be an adequate way of quantifying information. So it's a kind of vague intuition. It's not very clear. But anyway, so this function has, and then they consider a set of postulates and show that, this function satisfies that those postulates. And since then, this function has been studied extensively, but it wasn't noticed that this function also has this nice property that is monotone, non-increasing under TI operations, or time translation invariant operation. So this was noticed very recently, basically. So another maybe more famous example of measures of asymmetry is this function, which is called originally defined in this paper, and it's called asymmetry. At the time, this was the only known measure of asymmetry, so that's why they call it just asymmetry. So A rho is defined as S is the von Neumann entropy, G rho is the symmetrized version of a state, and by symmetrized I mean, let's say you randomly apply a time translation and average over the state. So the effect will be basically dephasing the state in the energy eigenbasis. We saw this function before in this workshop. So here is PE is the projector to an energy subspace with energy E. So PE rho P is just the phase version of the state in the energy eigenbasis, and S of rho is the entropy of the original state. So the idea is, well, asymmetry is again a very intuitive quantity. The state is breaking time translation symmetry if its entropy increases when you randomly time translate the state, basically. Okay, and later it was noticed that this same function is actually also can be understood in terms of relative entropy. We saw the notion of relative entropy in the previous talk. In particular, this function is equal to the minimum of or infimum of the relative entropy between state rho and the set of incoherent states. So omega is an arbitrary incoherent state here, and it's also equal to the relative entropy between rho and this symmetrized version of rho, and is equal to this function here. So this function is also sometimes called relative entropy of asymmetry, and this is in analogy with the concept of relative entropy of entanglement in the entanglement theory, or relative entropy of resource in general in resource theory. So in general resource theory, you can quantify the amount of resource as the minimum amount of relative entropy between your state and the set of freest states in the resource theory, basically. Okay. And this can be generalized also. Instead of this here, you have you apply basically a uniform distribution. Here you can have a weighted distribution. It's called the weighted Thoroughling. So you apply PT here is a probability distribution, and you can show that again this function is a monotone under TI operation. Okay. And it turns out that the kind of constraints that you obtain from this monotonicity of this function is independent of can be independent of the kind of constraints that you can obtain from the monotonicity of this function. Okay, so it turns out that, so I mean, I started by talking about closed system, and then I mentioned that in the context of closed system, Noether's theorem imply conservation laws, and then I mentioned that Noether's theorem does not apply to an open system, even if you have time translation symmetry. So one main motivation of studying this measures of asymmetry is to basically study consequences of symmetry in the context of, for the case of open systems. But it turns out that they are also useful even in the case of closed systems. So, you can show that basically in the case of closed system time evolution, let's say if state rho goes to sigma by a energy conserving unitary U, then we know that any measure of asymmetry for rho should be larger than or equal to f of h of sigma just by definition. But any energy conserving unitary process is also reversible you can if you apply a U dagger on the final state, you can get rho back, and again, because this function should be non-increasing under U dagger as well, you find that f of h of rho should be less than or equal to f of h of sigma, which means that this quantity is conserved. So this any measure of asymmetry should be a conserved quantity in any closed system dynamics with respect to symmetry. And in this, and of course we have also our standard conservation laws that are implied by Noether's theorem, for the fact that, for example, all the moments of Hamiltonian should be conserved. And it turns out that in general, this new conservation laws that are obtained by conservation of asymmetry are independent of the conservation laws that are obtained from conservation of the standard conservation laws that are implied by Noether's theorem. So these new conservation laws are independent of them. So I have an example here, but just in the interest of time, I will skip this example. And next, I want to talk about another idea, another method for finding the consequences of the symmetry of dynamics. Are there any questions so far on measures of asymmetry or?
I don't see any questions so far, so you can go on, I guess.
So the next idea is again a very simple idea, similar to measures of asymmetry, but it turns out to be useful. Is the idea of modes of asymmetry, or also called modes of coherence. And so here the idea is, it's just using Fourier transform for understanding the consequence of symmetry. It's a very simple idea. And in classical systems, let's say in classical, for example, in a linear amplifier system, the fact that the process is linear and invariant under time translation implies that if you have an input in frequency omega, should be at the output you should also have an output at the same frequency omega. You can only have and maybe an amplifying factor which can depends in general to the frequency omega, but otherwise the frequency cannot be changed. And this follows again from just the fact that the transformation is linear and time invariant. Okay, and now you can ask what you can apply exactly the same idea to the case of to the quantum case. So suppose I have a Hamiltonian like this. So here I'm assuming that so energy levels are equidistant, and the distance between any two consecutive energy level is delta E. Then you can write your general rho density operator rho in this form as a decompose it to these basically different modes omega, which goes from minus n to n, where each component in omega, rho omega, is defined in this way. So you only have terms which where the energy in this kit is J, and the energy in this bra is J plus omega. So the difference between this energy is just omega. In other words, to be more clear, you get basically these different shifted off diagonal terms. So omega equal to 0 is just corresponds to diagonal terms, and this is omega equal to 1, etc. You get all of this shifted off diagonal terms, and under this evolution under this Hamiltonian, each mode is basically just obtain a phase, e to the I omega t. So it's exactly like similar to the picture we saw before in the classical case. And now you can easily show that under general linear TI operation, each mode of the input is mapped to the corresponding mode of the output. So if rho is transformed to sigma, then the mode omega of rho is transformed to the mode omega of sigma. Okay, so each mode is just directly mapped to the other one. And this puts a lot of constraints on the possible kind of transformations that can happen in this way. Okay, so, and you can quantify this constraint. So in particular, so if this is 1 is just L1 norm, so you can argue that for any omega, the L1 norm of rho omega at the input is larger than or equal to the the norm of the component at the output, sigma omega. And in particular for this example that I'm discussing here, this implies this constraint. So this is again, remember, a constraint that's satisfied for all TI operations, and in particular is satisfied for thermal operations. So when you couple your system to a thermal bus by an energy conserving unitary, we know that all these constraints should be satisfied. Okay. Now, I want to talk about, I talked about coherence and how it can be understood as a, as a resource independent of work. Now I want to talk about coherence distillation. So this is a like more recent result. So the idea of coherence distillation is you want to combine systems which contain noisy coherence, combine them together, maybe perform some work or consume some work, and obtain states which contain coherence, but they are now pure or closer to a pure state. Okay, and so as I mentioned before, if you're allowed to use an arbitrary amount of work, if you can couple into a battery and consume an arbitrary amount of work, then this entire process can be modeled by a TI operation. Okay, so I can implement an arbitrary TI operation in this way. So now, so the question that I want to study is how well I can do distillation when I'm allowed to apply an arbitrary TI operation. And here is a more specific example to make this clear. Suppose each system is a qubit or a two-level system with this Hamiltonian. Z is again Pauli Z operator, and consider general mixed state of this system. Phi is this is actually not a general mixed state. Phi is just a state plus 0 plus 1. And rho is a noisy version of phi. So I consider this mixture with the maximally mixed state. And now suppose I'm given n copies of this noisy system, and I want to apply an arbitrary TI operation and try to basically purify its coherence. So ideally I want to generate a single copy of phi. I want to generate this state. And I'm allowed to consume an arbitrary amount of work, which means that, again, it means that I can implement an arbitrary TI operation. And so the question is, what is the maximum achievable fidelity that I can obtain here? So if I'm allowed to implement an arbitrary TI operation, what's the maximum of this number? And in particular, one very natural question is, can I distill a single copy of this state phi from finite copies of this noisy version of this noisy states or not? And I mean, a very natural tool to study this problem is just to use these measures of asymmetry that we saw before. And you can argue that, again, under TI operations, a measure of asymmetry should be non-increasing. And so, you need to make sure that the measure of asymmetry at the output is less than or equal to the measure of asymmetry at the input. Okay, and this should give us some constraint. But if you look at all those measures of asymmetry that I discussed before, like Wigner-Janovsky formation and asymmetry, etc., relative entropy of asymmetry, you can see that they all give you a finite number for this state. Okay, so it means that from their point of view, there is a finite n where the asymmetry of the input is larger than or equal to the asymmetry of the output, and so from their point of view, the transition should be possible in general for a finite n. But it's not hard to show that this is not possible. For to generate an exact copy of phi, you need infinite number of these mixed states. Okay? And to basically see this phenomenon, to show this phenomenon, I introduced a new measure of asymmetry in this recent work, which I call it purity of coherence. It's basically defined as trace of h rho squared, h rho minus 1 minus trace of rho h squared, when h rho h is in the support of rho, which means that basically when this quantity is finite, and otherwise it's just infinite. Okay? So this is the definition, and the way I obtain it is obtain it from second derivative of Petz's Rayleigh relative entropy for alpha equal to 2, or equivalently is related to a quantity that's called RLD quantum Fisher information, right logarithmic derivative Fisher information. And then you can show that this function has lots of nice properties. It's faithful, it's zero if and only if the state is incoherent, or which means it's diagonal and the energy eigenbasis. It's monotone under TI operations, and for composite non-jacking systems with uncorrelated state is additive. Okay? It's in particular is additive. However, when you look at the case of pure states, you can easily see that this function is either infinite, or if the state is energy and energy eigenstate is zero. So it's either infinite or zero. It doesn't look like such a useful quantity for pure states. But the point is, this function can capture this fact that I mentioned before, that the states, the pure coherent states, are in some sense unreachable. They are, in some sense, a pure coherent state have infinite amount of coherence. So in particular, you can show that if you can show that this purity of coherence is lower bounded by this VH of psi max. Psi max is the eigenvalue. P max here is the largest eigenvalue. Psi max is the corresponding eigenvector of rho. And VH of psi is in just the energy variance. Okay, so you can show that basically purity of coherence is lower bounded by this quantity. And you see that if a state has the maximum eigenvector, the eigenvector with maximum eigenvalue has a non-zero energy variance, then as Pmax increases, as it goes to 1, as the state becomes more pure, then this quantity diverges. Okay, and that's basically why I call it purity of coherence. And so if we go back to the example that I described at the beginning, the question of distilling coherence. So I'm given n copies of this state, and I want to distill a single copy of the phi. So the infidelity of the input state, infidelity is 1 minus fidelity. The infidelity of input state is 1 minus lambda half. And let's say epsilon n is the infidelity of the output state with this desired state phi. Is this quantity, and you can show that this scales like E lambda divided by n. So it's basically a scales like 1 over n up to some corrections with 1 over of order n squared, basically 1 over n squared. So, and using basically this quantity purity of coherence, we can actually find a tight bound for this error that can be achieved in coherence distillation. So here. As I mentioned, En scales like 1 over n up to a factor E lambda. And so n times En, n times the output infidelity, which is here, the vertical axis, is this E lambda, and it converges to a fixed number. And the horizontal axis is just the input infidelity, 1 minus lambda half. And then you can show that the infidelity, is lower bounded. Using this purity of coherence, you can show that the infidelity of the output should be lower bounded by this number like this, 1 over n, 1 minus lambda squared for lambda squared. And so this bound, interestingly, I haven't been able to show that this bound is achievable for all values of lambda, but I can show that it's achievable in two regimes where the input state is very noisy, so your state is almost close to the maximum mixed state, which will be this region, or in the regime where your state is very pure, which will be this region. Okay. In both regimes, I could find two different processes that basically distill coherence that and achieve this bound basically. So this will hold as equality. Okay, and now this is distillation in the single copy regime. So you're trying to distill one single output. But another interesting problem is what about distillation rate when you want to distill, many copies of the state? Is it possible to achieve a non-zero rate or not? So suppose I can consume again an arbitrary amount of work, and I'm given n copies of a mixed state row, and I want to distill m copies of a pure state phi with a vanishing error. So I want error goes to 0 in the limit n goes to infinity. And so the question is it possible to implement this transformation with a non-zero rate or not? And it turns out that the answer is no. So again, in this recent work, I've shown that the answer, you cannot distill for a generic mixed state, you cannot distill coherence with a non-zero rate. Okay, so I'm going to skip some details to go to the next part of the talk, which is about locality. So are there any questions so far in the?
No questions so far.
Okay, good. So now let's talk about locality. So now, if you were not interested in the notion of monotones or TI operations, you can forget everything so far except the notion of symmetry. I want to use the notion of symmetry again here. So here the question that I want to study is how you can implement an energy conserving unitary in general. Okay, suppose I have a composite system formed from different parts or subsystem, and I want to implement an energy conserving unitary on them. So I'm assuming that the total Hamiltonian of the systems is just, they are non-interacting with each other. So the total Hamiltonian is in this form. And I want to implement a general energy conserving unitary just by applying local energy conserving unitaries. I want to, for example, couple 1 and 2 together, 2 and 3 together, etc. And just by applying this local operations, local energy conserving unitaries generate an general energy conserving unitaries. And so the question is this possible or not, basically? Okay? And intuitively, you may expect that, well, if you think about it classically, just by a sequence of two local energy conserving operations, you can redistribute energy in any way you want. You can, if you want to bring energy from here to here, system 1 to system 2, you can first bring it to system 2 and then system 3. So this locality constraint should not restrict me, and I should be able to do any arbitrary energy conserving unitary using just two local energy conserving unitaries. And so just to be more concrete, let's focus on particular examples. Suppose I have n qubits with this Hamiltonian. So this is the total Hamiltonian. And then unitary B is energy conserving if it satisfies this symmetry, basically, if it leaves this total Z invariant. So this is basically U1 symmetry. So let's think about some examples. If I have just one qubit, then what are the energy conserving unitaries? It's a very simple, boring set. It's just diagonal unitaries in Z basis. If I have two qubits, then in this sector 0, 0, you can have arbitrary phase. In this sector 0, 1, 1, 0, this is a sector with a given energy of the system. You can have an arbitrary 2 by 2 unitary, and in this sector you can have again an arbitrary phase. And for n equal to 3, you have more complicated. You have 4 different sectors. Again, these are 2 arbitrary phases in this sector with 0, 0 and 1, 1, 1. And then you have arbitrary 3 by 3 unitaries in this sector and these 3 sectors, basically. And now the simplest version of the question that I want to ask is this question: do 2 local energy conserving unitaries in this 3 qubit system generate all energy conserving unitaries or not? If I first couple these 2 qubits and then these 2 qubits and these 2 qubits, etc., by using energy conserving unitaries, can I implement an arbitrary energy conserving unitary or not? Okay, and this is related to a result that is extensively studied in quantum computation. In quantum computation, of course, we always deal with this problem of implementing a general unitary transformation. And according to a standard result in quantum computation, you can show that any general unitary can be implemented by a sequence of 2 local unitaries. So these are unitaries that act only, by two local, I mean unitaries that acts only on two qubits or two qubits or two subsystems in general. Okay, so any unitary transformation on a composite system can be realized exactly. So there's no approximation. You don't need any approximation or errors by finding a sequence of two local unitaries on the subsystems. Okay. So basically, the question that I'm asking is whether this universality result that holds that holds in the absence of symmetries, does it remain valid in the presence of symmetry or not? If I impose the constraint of symmetry and I ask all these unitaries should respect the symmetry, can I still implement a general unitary or not, a general symmetric unitary or not? Now, I phrase this question in terms of unitary transformation, but equivalently, you can phrase this question at the level of Hamiltonians. So suppose I have a general Hamiltonian HT. So this is a system with multiple parts, and so this is the so HT is the Hamiltonian, which in general can be time dependent. And suppose this Hamiltonian can be written as sum of k local terms. HRT is k local. Again, k local means that this term HR acts only on k subsystems and non-trivially only on k subsystems and acts trivially on the rest of the systems. Then you can show that, and let's assume that basically HT satisfies this symmetry, okay? So it's depending on, how you interpret this operator ZG, it can have different interpretation. For example, it can mean invariant under rotation around Z, or if you just interpret ZJ as the intrinsic Hamiltonian of the system, each system, you can say this is an interaction that conserves the total energy of the subsystems, basically. And now think about the unitaries that are generated by this under Schrodinger equation. So initially, I have this initial condition V0 equal to identity, and think about this family of unitaries. So the set of unitaries that can be generated in this way by k local interaction is exactly the set of, equal to the set of unitaries that can be implemented in this way by applying k local unitaries. So it's instead of studying this question, I can basically study this question. These two questions are equivalent. Okay, and now here is the result, the kind of surprising result, at least for me, is the fact that in general, in the case of continuous symmetry, like U1 example that I mentioned before, a general symmetric unitary cannot be implemented using local symmetric unitaries. And in fact, you can show that even if you can do, even with k local symmetric unitaries, you cannot generate a general k+1 symmetric unitary. You cannot even go one step higher. You can generate some k+1 local symmetric unitaries, but you cannot generate them all. Now, you may ask that, well, that maybe, I cannot implement these unitaries exactly, but maybe I can implement them approximately. Okay? So maybe I can get arbitrarily close to a desired energy conserving unitary. But interestingly, it turns out that even this is not possible. And to understand this, is useful to think about the geometry of this set of unitaries that you can implement. The set of all energy conserving unitaries, or the set of all symmetric unitaries, versus the set of those energy conserving unitaries that can be implemented by two local unitaries. Okay, and this figure basically represents explains the schematic relation between these two groups. You can show that they are both compact connected Lie groups. And so here the torus corresponds basically the group of all symmetric unitaries or all energy conserving unitaries. And the blue curve corresponds to the subgroup generated by two local energy conserving unitaries. Okay? So they are both compact connected Lie groups. And it follows that basically, and in general, the dimension of this the subgroup generated by two local or k local energy conserving unitaries is strictly smaller than the subgroup of all, the group of all energy conserving unitaries. And it follows that you can even, for generic energy conserving unitary, you cannot even get close to that. Okay, and so if you recall,
yeah, no, sorry, man, you have 10 more minutes, including question.
Okay, okay. I will
just to let you know about the
it
time.
just around 5 minutes. And if we go to back to this original, in this special example that I mentioned before, do two local energy conserving unitaries generate all energy conserving unitaries? For this case, even in this simple cases, the answer is no, right? With we cannot generate all energy conserving unitaries on this 3 qubits. It turns out that all energy conserving unitaries is a 20-dimensional manifold, and the subgroup generated by two local energy conserving unitaries is a 19-dimensional manifold. In particular, you cannot, for example, implement the family of unitaries, this family of unitaries, e to the minus I theta z tensor t, which is tensor 3, which is all energy conserving, and except finite set of points. You can, for example, implement this for theta equal to 0, but you cannot generate it. You cannot implement the general family of this general family of unitaries. Okay, and so the last result that I want to discuss is, well, this is a no-go theorem. It's kind of it actually made me kind of worried because there's a lot of results about in the ratio C of quantum thermodynamics and the ratio C of asymmetry, assuming and the first assumption is that all energy conserving unitaries can be implemented with a negligible thermodynamic cost, basically, and but interestingly, it turns out that you can circumvent this result if you allow use of an ancillary qubit, which in some sense can be interpreted as a catalyst here. So in particular, you can show that consider a finite set of closed systems with the property that for each system, the gap between any consecutive pair of energy levels is delta E. Then any global energy conserving unitary transformation in these systems can be implemented by a finite sequence of two local energy conserving unitaries, provided that one can use a single ancillary qubit or a catalyst with energy gap delta E between its two levels. Okay, so you can, if you are allowed to use this ancillary qubit or catalyst, then you can circumvent this no-go theorem. So in particular, if you think about, again, this qubit example, if you're allowed to use this ancillary qubit, which is, let's say, initially in a state 0, then using just interaction XX plus YY, you can implement and local Z on this ancillary qubit, then you can implement a general energy conserving unitaries on this N qubits, basically. So these green qubits are my main system. This blue one is the ancillary qubit that I use. Okay, and I think with this, I can now summarize my talk. I basically explained in the first part of my talk, I talked about this idea of, finding consequences of time translation symmetry in quantum thermodynamics, what kind of constraints we can impose on the, on time evolution of a system that respects time translation symmetry. And so I talked about basically different tools or different ideas for characterizing these constraints, the idea of measures of asymmetry and modes of asymmetry. And then I talked about the problem of coherence distillation, and I introduced this particular measure of coherence that basically can see why pure coherences are unreachable, basically. It basically shows that in some precise sense, the coherence content of a single qubit can be infinitely large. And the second part, I talked about how we can implement a general energy conserving unitary and a composite system. And I showed that locality leads to some constraints, non-trivial constraints on the family of unitaries that you can implement. But if you are allowed to use an ancillary qubit or catalyst, you can circumvent this no-go theorem or constraints. Okay, with this, let me stop here, and please feel free to ask questions. I can stay longer after the talk if there are discussions or questions. Thank you.
Okay, thank you very much, Iman, for this very nice talk. Is there already question? Otherwise, I have a couple of questions. Let's see, I see already one question and one raised hand. So yeah, Gonzalo is asking, so yeah, thanks for the nice talk. Regarding distillation of coherence, I was wondering how the results depend on the assumption of the setup. In particular, what if the final target state is not pure, or if you allow initially a product of different states?
Yeah, that's a good question. so so it's, I mean, depends on if the question is about the single copy or two or infinite copy regime, basically. So let me go back to this. Here. Okay, so so there were two different types of results here about the single copy. So when you want to distill a single copy, then you can't distill a, you know, an exact copy of this, but you can distill an noisy version of the state. And so, and then again, this bound gives you a tight bound. The bound obtained by purity of coherence gives you a tight bound for coherence distillation. So in this regime, when you want to, you know, distill many copies of the a pure state from many copies of the mixed state from at the non-zero rate, then you're right that if you assume that the state is mixed, so instead of, you know, distilling this pure state, I distill a more pure but not, you know, a state that is less mixed than the input, basically, right? But it doesn't need to be exactly pure. Then you can achieve a non-zero rate. So then this will be possible. And you know, you can you also asked about the case of product state. Again, it depends on the you know, the setup, but in general, this no-go theorem applies. So the no-go theorem, more precisely, I didn't go through the details, but the no-go theorem implies that if the projected to the support of a state, to, you know, the subspace spanned by the eigenvectors with non-zero eigenvalue, if this projector commutes with the Hamiltonian, then this rate will be zero. So now it doesn't matter where you know, the state is product or not. When this condition is satisfied, then the rate is zero.
Okay, thank you very much. I think that answers the question. And so we have also questions from Thiago. I think you are able to unmute yourself. So
Hi.
your question.
Hi, and thank you for your talk. I mean, I'm not very familiar with this subject, so maybe this is a bit silly, but I mean, in the beginning, you defined this translation invariant operation, which the one that it's similar to first applied time evolution. But I mean, isn't at the end all this time this time translation, all these evolutions at the time invariant, all of them given by the time evolution, hr minus I ht. My question, I mean, is this any operation that is time translation should be given in this exponential form of the Hamiltonian, no?
No, for example, what if, so I guess you're talking about a closed system, right?
Yeah, yes. I mean, I think so, like because H is the generator of the group, you know, somehow.
No, if let's say if the Hamiltonian is degenerate, if it has a symmetry, then you can have, you know, operators that are not in the form of H and still commutes with H, right? So, for example, if you have, you know, my Hamiltonian has rotational symmetry, then you can add some perturbation that breaks that symmetry, that rotational symmetry, but it still commutes with the Hamiltonian. Right? So that's, of course, one way to, you know, just one way of constructing counterexample. But even if my Hamiltonian is not degenerate, you can think about Hamiltonians which are, for example, think about the Hamiltonian which is h squared. So e to the minus I h squared t still commutes with this unitary and still, but it's not, you know, it's independent Hamiltonian basically.
Okay. I mean, one last question. I mean, just in this final part about that you can build the general symmetry from the local ones. Yeah. It just came to my mind that, I mean, when you have this problem that you also want to simulate like a spin chain where you have two body interactions and you try to break it in two local gates doing this Trotter decomposition, yeah. Then you see that you cannot do exactly also that. I mean, is this related somehow? I mean, the fact that you cannot evolve this Hamiltonian break it into gates like in the quantum
So,
decomposition.
right. So are you talking about the error that appears because of link
Because they don't commute, yeah.
Yeah. So, I mean, you're right. This is not related to that, and so the point is that error, you can get rid of that error if you know basically that error is not fundamental. And this basically one way to think about it is just follows from this universality result that I mentioned here, that it's related. It's not exactly the same thing, but it's related that to the fact that you can implement a unitary exactly without any error just by two local unitaries if there is no symmetry. So the error that you described there is not a fundamental error. It's just, and by fundamental, I mean it's just a consequence of this particular totalization procedure that you're using.
Okay, thank you.
Okay, we have one question from Marty. So Marty, you can speak.
Okay, yeah, thanks for the very nice talk. What I was wondering, so in this case that you showed that the rate goes to 0 when you try to get, so say the many copies scenario that also Gonzalo was asking about. So when you want to convert, so if you would like to go from a mixed state, somewhere here. So if you would like to go from a mixed state with coherence to another mixed state with coherence, so I guess then you would have a finite rate. And I was wondering because in writing quantum thermodynamics, in resource theory, in this limit, you get the free energy as the relevant quantity. So I was wondering here with this, with coherences, what would be the relevant quantity?
Yeah, that's a good question. So I know that, if you go from purest, so if you think about the reverse direction, which is called, so basically you want to prepare this mixed states from a pure state. Then the optimal rate of transformation, the opposite direction, is just given by quantum Fisher information. The standard quantum Fisher information, also called SLD Fisher information. But in general, I don't know, so if you can, so the point is, in the setup that you are defining, I don't know if you can get a universal answer similar to the, the result that you mentioned on free energy, because, you have to choose, you have to pick one, random state as your standard state that you want to distill, basically, and the result will depend on that. Now, I don't know if you can make this, you can extract a universal quantity from that is somehow independent of your standard mixed state that you're choosing. I think that's a good question. I don't know if you can extract, but at least I know that in one special case, as I mentioned before, that when you go from this pure state to mixed state, then the optimal rate of transformation. In other words, the cost of, you can ask, what is the cost of preparing this mixed coherent states from pure coherent states? And that's given by the quantum Fisher information of these mixed states.
Okay, thanks a lot.
Sure.
Okay, just a very quick question from my side. So you were just speaking of quantum Fisher information. It's respect to time.
Yes, exactly.
Okay, thank you.
The family of time. So this is quantum Fisher information for the family of time evolved version of the state, basically.
Okay. So we have one more question from Felix. So is there an easy or intuitive characterization of those global symmetric unitaries that cannot be implemented with locally symmetric ones? Are they somehow unphysical?
Yeah, that's a great question. For special symmetries, and the specific representation of symmetries, I have I know the answer, but I don't know in the general case. Like, for example, in the case of, in this case that I discuss here, I have characterized all diagonal Hamiltonians, right, that can be implemented using k local energy conserving or symmetric unitaries. But I don't know a general method for characterizing it in the general case. And regarding your second part of question, is it unphysical or not? I don't think you can call it unphysical. Is, the family of this family of unitaries, e to the minus theta z tensor 3, is it, do you think this is, I don't think we can call it an unphysical thing, an unphysical family of unitaries. So the point is, just because of this constraint of locality, with two local unitaries, you cannot implement them. And if you allow me to use an ancillary qubit, then I can implement them. So I don't think you can characterize them in some sense as unphysical. But the point is, this, this can give you, again, an interesting non-trivial constraint. So if you know that your Hamiltonian, this result basically means that if you know that your Hamiltonians is two local and has certain symmetry, for example, it's invariant under rotation around Z. And I think, I can use this diagram here to explain it. So if I know that the Hamiltonian has both locality and symmetry, so it has both locality and symmetry, then this result means that in addition to the standard conservation laws, the knowledge theorem conservation laws, there are some additional constraints on the unitaries that can be implemented by this, right? So in other words, the standard universality of two local unitaries implies that locality alone, locality of Hamiltonian, doesn't impose any constraint on the unitaries that you can implement. Symmetry, we know that it just implies conservation laws. Symmetry of Hamiltonian implies the unitary that you generate is respected symmetry, and it satisfies conservation laws. But symmetry and locality together, there are some additional constraints here. I haven't fully characterized it, but I know that for certain cases. And now I think this additional constraint could be useful for understanding, if for example, for understanding a chaotic or chaotic behavior of a many-body system, because they give you extra constraints on possible time evolution, which is a consequence of both locality and symmetry.
Sorry, can I just maybe question or comment on this example? Because you see, when you're having like an arbitrary unitary and you decompose it to the universal set of gates, what you have here is much more restrictive, because when you have your conservation of essentially of number of excitation or magnetization, you essentially have only two operations which are allowed here. Yes, you can have a arbitrary two-particle swap, or you can have a Z-gate, speaking on the quantum information language.
So are you talking about this example, right?
Yeah, about the example and the fact that you cannot even expand the...
It's a little bit more than that. It's a little bit more than that, because you can have, in this sector 0, 1, 1, 0, you can have arbitrary 2x2 unitary. So, this is not, you can have, for example, ZZ interaction.
Yes, you can have ZZ interaction, but two ZZ's interaction is just a product of Z1 on Z2, for example, yeah?
Yeah. And you can have
this is...
Sorry, go ahead.
Sorry?
And you can have XX.
Yeah, you cannot have like XX or YY, you can have only some, which will give you flip-flop. But if you look on the universal set of gates, it's much wider, because essentially in universal set of gates, in a simple case, you get a C0, which is essentially equivalent of your flip-flop, because you take 3 C0s, you get a flip-flop. No, but you get an arbitrary single qubit operation. Here you don't have it because of your symmetry constraint.
I actually do not agree with this, because well, let me see which part I don't agree with. So the statement that you have much larger families of unitaries in your universal gate set. Let's say if you add just one single qubit gate, to the family that we are describing, one single qubit gate that breaks the symmetry. Let's say not an arbitrary gate, but let's say, for example, I think T gate. Well, not T gate, but there you can find a single qubit gate that if you add just that one to this set, then you suddenly get all the unitaries. So in that sense,
because you can simulate, because if you do that, in that case you're probably able to simulate arbitrary single qubit gate, and in that case you cover the set.
Exactly. So I just want to say this is not much smaller. If you just add one thing, then you get suddenly the full universality.
Okay. Okay,
So,
thank you.
sure.
Okay, I don't know if there is more question. I have some question myself, but maybe I might better send
I
you
can
an
have.
email.
I'm free now, so I can stay and type more.
Okay. Yeah, no. So maybe I will focus on the maybe the main one. Yeah. So yeah, maybe to start with, so there are, to put like a context, there's some recent results. So establishing like the thermodynamic cost of measuring time. And so they show that in particular, if you want to measure time, you have to have entropy production and also a waste of energy and something like that. I mean, which is quite intuitive. But at the same time, so if you look at framework as the one you presented, so you have only unitary operation, which on top of that are respect I mean symmetric about with respect to the time invariance. And so yeah, my question is, so if you have coherence, then you should, at least theoretically, you should be able then to measure time, because you are not anymore time invariant. And as you just said, you also have a quantum Fisher information with respect to time, which is different from zero. So yeah, I just wanted to have your point of view of that. Do you think it's because, yeah, the experimental issue of that, I guess, it's that if you want to measure time from coherence, you need to have a reference of phase in your experiment, and that might be, I don't know, complicated. Or
Yeah.
so yeah, I just wanted to have your view of that.
Yeah, I mean, this is of course a very, big area in. It's related to this area of quantum reference frames, basically. As you said, of course, it depends on how you want to define measuring time. What do you mean by measuring time? Do you mean time interval, or you mean time with respect to a reference clock? But you're right. I mean, and this is not just an experimental requirement. There's a fundamental reason that you need you need to a reference. The phase reference that you're talking about there is just basically play the role of your clock reference, your reference clock, basically, and you're measuring time with respect to that reference clock. So, and it's certainly related to the topics that I'm discussing here, and this relation is, at least to some extent, is studied in the context of quantum reference frames. I don't know if you have a specific question on this, or.
Yeah, not really. Yeah, it was, I mean, what I found it interesting in this idea is that, yeah, so again, there are all this work showing that if you want to measure time, you need entropy production and
That's
things like that. And so so assuming this would be you would be able to measure time, you would have something different because you don't have entropy production, and what's more, you are able, or you would be able to measure time only if you have coherence. So you will have something like a quantum effect that if you have only population, you are not able to measure time, but if you have quantum coherence, you would be able. But yeah, as you more or less said, apparently I mean, yeah, you would be able maybe to measure only time interval and not the absolute time. So maybe it's not so interesting. I don't know.
I'm not familiar with this recent works that you're describing about entropy production in this context, but I think this general question is certainly related to the formalism that I'm describing. Actually, this formalism is sometimes called resource theory of quantum reference frames. you know, the relevant reference frame here in this example that we are discussing here is just a clock or a phase reference. And yeah, so
yeah, if you're interested, I can send you
I'm different.
one or two people I have in mind, and we can even discuss more of that.
Yeah, sure. Yeah, I'm certainly interested.
And also, again, there's also, on top of that, there's also this argument of quantum Fisher information. If the quantum Fisher information with respect to time is different from zero, principle, you should expect that you can extract information. I mean, your system has information, contains information about time. So you should be able to, at least to some extent, to use that.
Yeah, exactly. Just one minor comment that I have here is, I mean, it's always interesting to ask which, you know, whether this constraints that we are describing here, whether there are some classical analog for that or not. And, you know, classically also, you know, you have the, you need to interact with the reference clock, you know, to measure time, basically, or to prepare a state which is time dependent, a distribution that is time dependent. You need to interact with the reference clock. And so it's always interesting to see, you know, which aspects of this problem that you're describing, entropy production in particular, has classical analogs. So I'm certainly interested to learn more about it.
Okay, all right. So yeah, I'll send you the people I have in mind, and yeah, we can discuss more.
Okay.
So thank you very much for your very interesting talk. Thank you also obviously to Gabriel for also his nice talk, and for the participant to stay. I was about to say that late, but yeah, again, depending where you are, it might not be so late.